Welcome, everyone. For today's prep, we're going to be looking at velocity. So we're going to be looking at average velocity and start looking at something called instantaneous velocity. So to begin, we're going to start with our little introduction to the concept of velocity. And it comes down to an object moving in a straight line. So the setup here is we're going to have a function. We're going to call it a position function. And this is a function s of t. And what it does is it tells us the position or the location for an object that's moving in a straight line at time t. So it tells us where our object is at any given moment in time. So we're going to be looking at the case where we have an object and it's just bouncing around along a straight line. And when we do this, the way the position function works is it's telling us the position of our object relative to a specific reference point. And normally, this is the origin. And what happens is relative to this reference point, we're watching where our object goes. So our object might be bouncing around and might go to the right, and then once it gets far enough, then it kind of starts back, and it might travel to the left, or it might bounce around a bit. But it's stuck on this line, so it's just bouncing back and forth along this line. And when we do this, we have our reference point, normally the origin, and then there's two directions. So normally we give one of them we make one of them the positive direction. So a lot of times that's to the right, but not always, or up. And then there's also a negative direction. A lot of times this is either down or to the left, just like the x-axis and the y-axis. The x-axis, there's the positive direction, the negative direction. The y-axis, there's the positive direction and then the negative direction. So a lot of times, if we're looking at a horizontal line, a lot of times the positive direction is to the right and the negative direction is to the left, but not always. And so a couple examples of motion in a straight line, we're going to be looking at things. You can think of it like a particle that's moving a straight line, or you can think of it as a car that's just driving down the highway. So driving on a straight road. Or the other case we're going to consider is for like standing on a cliff and we drop a rock off of the cliff and we watch the object kind of just fall to the ground. So, effects of gravity, that kind of thing. So maybe like a rock due to gravity. These are going to be really the two examples to keep in mind. And the question that comes up is a natural question is how fast is that object moving? Now how do we actually measure how fast something is moving? Well, what we're really doing is we're measuring how far the object travels over a given amount of time. And this is called the average velocity. So the average velocity is the displacement of our object that's moving divided by the amount of time that has gone by, the time that's elapsed. And so when we do this, we're going to be saying the average velocity over a specific time interval. And we might write our time interval like this, from A to B. And when we do this, A is going to be the start time. So we're watching our object move around. And how we're going to calculate how fast it's traveling is we're going to kind of pick a time where we're going to start measuring. So at that start time, we're going to record where it is. So we're going to record the starting position of our object. So our starting position, we're going to record where does it start. And then our object's going to be moving around, maybe bouncing back and forth. Maybe it just goes all in one direction. Doesn't matter. We're just going to watch what our object does. And then we're going to pick an end time where we record where does our object end up. So what's the ending position of our object? So we have our starting position and we have our ending position. And that's what this average velocity calculates. It's calculating how far did our object move divided by how much time did it take. And the issue with this, though, is this doesn't tell us the specific velocity at a given moment in time. What this does is it tells us the average velocity. So during this time interval from A to B, it might start off traveling really fast, and then towards the end of that time interval, maybe it slows down a bit. And what we're seeing then is the kind of the average effect. So maybe it starts off going really fast, and then towards the end it slows down. What we're getting here, we're not really seeing that. What we're seeing is just the average of the results. So we're interested in knowing what the instantaneous velocity is. How fast is our object going at a specific moment of time? And this is, kind of a natural question. We're kind of used to it. If we think of driving in a car, we can look at the speedometer, and that speedometer is telling us how fast we're traveling at that given moment in time. So we know how fast we're going. So how do we actually measure that, though? Well, the idea is we're going to look at this average velocity, but we're going to look at a very short time interval here. And that's going to give us our instantaneous velocity. So the velocity, v of a, v for velocity, and this is the instantaneous velocity, but we just abbreviate this. We're just calling this velocity. So we'll specifically say average velocity when we're asking for average velocity. But when we say velocity, what we mean is the instantaneous velocity. So this instantaneous velocity, v of a, is giving us how fast our object is traveling at that specific moment, t equals a in time. And the idea here is our velocity at time a is going to be the limit as b approaches a of our average velocity. So what we're doing is this is our average velocity that we just looked at. This is our average velocity. And what we're doing is this gives us a pretty good idea of how fast we travel, but over a kind of an extended interval of time. What we're going to do is we're going to shrink that interval of time. We're going to shorten it up. And that's what this limit does. So this limit, we're letting our ending time get closer and closer to our starting time. So when we think about our time interval, it almost helps to kind of just picture this as an interval. So we have our start time on one end, and then we have our end time on the other end. And what we're going to do is, this is our interval of time here. What we're going to do is we're going to take this end time and we're going to shorten this interval up. We're going to move that ending time closer and closer to the start time. So what we're doing is we're getting as we calculate this limit as b approaches a, we're going to be getting the average velocity over a smaller and smaller time interval, so that once b is really close to a here, we're going to have the instantaneous velocity at that specific time t equals a. And so essentially this is the limit as b approaches a of our average velocity over that time interval from a to b. That's really what we're doing here. Now, this version is perfectly fine, but to really kind of illustrate what's going on and to make some of the calculations a little bit easier, we're going to do a kind of a change of variables here. So rather than using b, what we're going to do is we're going to say b is equal to a plus h. So what h represents is it represents the length of our time interval. So h here is the length of the time interval. And so the idea here is when we let b equal a plus h, if we kind of fill that in, we get s of a plus h minus s of a. And then in the denominator, we get a plus h instead of the b, and then the a's cancel, leaving us with just that h. So this version of this limit, these two are equivalent, but this version kind of illustrates that if we're thinking of h as the length of our time interval, what we're doing is we're calculating this limit as that length goes to 0. So as we're using shorter and shorter time intervals here. All right, so let's try an example. And we're going to look at just the first part of example 1. So suppose that a rock is dropped from a height of 50 meters, and the position function here is s of t, which is 4.9 times t squared. And we want to, for part A, we want to find the average velocity during that time interval from 1 to 2. So the average velocity over that time interval from 1 to 2, let's write out our formula. So it's our ending position. So it's the position function evaluated at the ending time, minus the position function evaluated at the starting time, divided by the change in time. So 2 minus 1. So it's change in position, which is also called displacement, divided by change in time. All right, so all we got to do then is plug 2 into our position function. So we end up with 4.9 times 2 squared. And then subtract off, and let's plug 1 into our position function. So we get 4.9 times 1 squared. And then all over 2 minus 1, which is just 1. And if we simplify this down, we end up with 4.9 times 3. And that ends up being 14.7. Now, when we're talking about velocity, we just have to be careful if units are given. So if units are given, we have to use units in our answer. So in this case, well, units are kind of given. And, well, they're actually given in part B. So our distance, though, is being measured in meters, and our time here is being measured in seconds. So when we calculate average velocity, the numerator here is a distance measurement, and our denominator is a time measurement. So our units for velocity are going to, in this case, be meters per second. All right, so that's how to calculate the average velocity. And this should kind of feel similar at this point. We've done this kind of thing when we looked at tangent lines. This is really just the slope of a secant line. So it's the change in y divided by the change in x, essentially. So that's going to come. We're going to come back to that. But in class, we're going to see how do we use our limit definition to calculate the instantaneous velocity at this specific time. So we'll see you then. Bye-bye.